of where it could go. And in order to save us trouble, we will draw up until we get to the resonance structure that gives us the answer we need to know. Okay, otherwise we could be drawing resonance structures all day here. So we're just going to draw until we get to the one that's important. You guys just need to understand there may be others. Okay, but we'll just do the one we need to focus on. So, here we go. Let's, I'm actually going to spin the electrons around. You'll see why in just a second. It seems like a minor change, but I wanted it that way. All right, we're going to put this guy first, ortho, and then we'll draw meta, and then we'll draw para. So here we go. Let's do ortho first. I'm going to have these electrons here on the side come out and attack. And try to be consistent with me. Normally it won't matter. For this discussion it does. Okay, so the ones that are straight up and down are coming out and attacking. And we're going to draw this thing attached ortho. So here's OR. I'm going to go back to OR. I'm too lazy to do CH3. Here's this. And here's this. The gas may be off actually. Okay, you'll have better luck now. And our electrophile will be right here, and the plus will be right there. And then what we're going to do is we're going to start drawing resonance structures. So, I'm going to flip electrons in the ring over that way, and we'll draw that sigma complex. So it's going to look like this, OR, electrophile, the plus is there. So far there's nothing special about this. Any of the ones I've drawn. They're somewhat stabilized because in general, this oxygen can donate electrons to the ring. So the sigma complex is better than if the oxygen weren't there, but there's nothing really special about the ortho position yet. That argument could be applied to meta and para as well. So let's draw another one. This last one I drew is the key one that tells us why that group going ortho is a good thing. Does anybody see why?
More stable tri-substituted.
Okay, it's tri-substituted, right? But it's better than that. I could make that argument with an electron withdrawing group, okay? And so that's not the argument that's going to work for us. It's better than that.
Oxygen.
The oxygen has a lone pair, right? The plus is on the carbon right under the group that can donate electron density. So I can draw another resonance structure where the oxygen can donate electrons down and help to stabilize that positive charge. So in the ortho position, I get a resonance structure that's really good. This is a very stable structure. So that's a good thing. So it makes sense that an activator would go ortho, because I can get the plus right underneath the activating group, which helps to stabilize it. Okay, let's try meta. So what we'll do, same thing we were doing before. We have our OR. We'll have those same electrons attack. And we'll put the electrophile in the meta position this time. And that puts the plus up here. Nothing spectacular about that. So what we're going to do now is we're going to just spin electrons around and see if we can't get that plus in a good position. Okay, so this first one, it's not bad, but it's not great. So we'll go OR, here's our electrophile. I'll just flop those over. I have this and this, and the plus is there. That didn't do the trick either. So let's try the next one. I'm out of options at this point. I drew all three. And none of those three was especially stable. So when the electrophile goes meta, none is especially stable. So what that tells us is that if you have a choice between ortho and meta, the group would prefer to add ortho because it gives me a much more stable resonance structure. So it's going to have a lower activation energy going ortho versus meta. With me so far? Okay, let's do para. Para, we're going to have a different set of electrons grab. We will have to have these bottom ones come out. And we'll put the electrophile there in the bottom. There, there. And my plus is here. Nothing fantastic about that. So we're going to have to start drawing resonance structures again. I think we can quit after this next one. There we go. There it is. So we're happy with that. Puts the plus right underneath the electron donor, and that's good. So when you have an activator, adding ortho or para puts the positive on the carbon attached to the electron donating group. That is much more stable. And that's going to be the preferred position if you have an activator on the ring. Okay, so all those things above the halogens are going to add ortho or para because they're good activators. Yes?
Is there a force left between the two?
Oh, as far as the groups go, yeah, there is. And we're going to see it at the very end of the discussion. Where it comes into play, I think your question, is if you have, like, say, two groups on there already and you're adding a third, there is sort of a tug of war. And the question is, well, which group wins? And so we're going to learn rules to deal with that. There is a preference, though. But you only really have an issue there if you have two different, like, opposing directing effects. If that makes sense, then one has to win over the other. And we'll see how to do that.
But as far as this goes, ortho pair.
As far if it's an activator, it's an ortho para director. Okay?
Is one of them better than the other? Like the
Nope.
para does in one step?
Oh, I see what you're saying. I see what you guys are asking. No, in terms of the resonance structure, one is not better than the other. In terms of going into lab, if you went into lab and you did a reaction and you get ortho para, oftentimes you see more para than you do ortho. Okay, why is that, do you think? Steric hindrance issue, yeah. You're looking at, you have a fairly large group up here, and putting a group there is just sterically not as favored. Okay, so like the reaction you guys are going to do today, you are using acetanilide, which looks like this. And if you take a look at your list, that's a strong activator. It's an amide. And it directs ortho para. And there is going to be a lot of evidence in the IR, and I think we're going to do an NMR of this guy, for nitration para. Very few of you will see any evidence of it being ortho. So it does ortho para on paper, right? In real life, para is favored. Okay, pretty strongly.
Does it do the dissociation?
You know, it depends what group you add. So the nitro group is a strong deactivator, if you look at your list. So I'm adding a deactivator, which means it's going to slow down any further reaction. But if I were to add, say I didn't add a nitro, say I added this to it, Well, then I just added an activator, right? So my ring's even more active than it was initially. And then you start to see di-tri substitution. Okay? But today we don't have to worry about that. All right, ready for deactivators? Let's do it. I'm going to use my same basic picture here. Wipe these out. Okay, let's put, I don't know, let's pick a good deactivator. Let's put a ketone on there, I guess. Why not? There it is. And we are going to do the same thing. We'll look ortho, meta, and para. So this guy right here is an electron withdrawing group. Okay, it can take electron density into itself. The carbon also has a delta plus on it because that oxygen pulling electron density away from it. So it's a definite electron vacuum. So let's go ahead and let's add a group ortho. Here's my electrophile, there's ortho, and we're going to draw these resonance structures again. C double bond R. What's the plus there? That's okay. You know, I now have a plus on a ring that has an electron withdrawing group on it. So that's not spectacular, but this isn't the worst resonance structure in the world, right? It's just, it's not great. And that's why this is a deactivator. It gives us an intermediate. I've got a plus on something that's electron withdrawn. So it's not spectacular. These are going to be real slow. Let's move things around. Plus there. Nothing really worse about that than the first one. And we'll move this down. Okay, so there are my three structures. Now, one of these is not like the others. Which one?
The one that has a hole in it.
But the last one has something really bad about it. What do you see there?
The hole with no electrons.
A hole with no, like, well, they all sort of have that. I have a plus right here, right? And I have a carbon that has a delta plus right there, right? So I have a positive carbon right where there's an electron withdrawing group. And that is not good. And all we have to say about that is, this is very bad. Okay, that's very, very destabilizing. So it is terrible with a deactivator, an electron withdrawer, to have a group go ortho. It's terrible. All right, let's look at meta. There, and I am going to just draw a whole bunch of benzene rings. I just drew a whole bunch of skeletons right there. And let's figure out where things are going to go. First one, I have electrons like that, and I have my plus right there. Okay, nothing really terrible about that. Nothing great, but nothing really terrible. So let's move things around. Again, nothing really absolutely terrible. Move things around again. these is all that bad. So what we can sum this up, we can say none is great. So let's say no structure. How about this? No structure is great because I have a plus charge on a deactivated ring. So nothing that I've drawn is where you look and say, wow, that is so stable. Okay, that's not the case. That's why it's a deactivator, it's slow. But, here's the but. But, no structure is really terrible. So this is like the best of a bad thing. Okay? It's if you're gonna have to do it, this is the one you'd want to do. Okay? So, meta's looking okay. Let's check out para. There. Put our electrophile para. We have this and a plus there. We'll flip electrons down. And that's as far as we need to go. So putting the electrophile para, all I have to say about this structure, yuck. Not good. Okay, so we can sum up a deactivator like this. When a deactivator is on the benzene, no structure is stabilized. Okay, none of them is stabilized. That is why it's a slow reaction. But the meta is the least bad. That's not saying much. Okay, but if you have to do it, the meta hurts the least. And so that's where it goes. Okay, everyone clear on that? Alrighty. Now let's go ahead and take a peek at halogens real quick. We'll only do one example. I think that's all we have to do to show this. And you guys will see why halogens are a little bit odd. Halogens are an exception. They are deactivators because they are highly electron withdrawing. Okay, that's inductive. So having a halogen on the ring is going to slow it down somewhat. They're not really, really strong deactivators because the inductive effect is kind of weak, but they are deactivators. Here's the exception. But they direct ortho and para, which is a little bit weird. So let's take a look just at an ortho one, and I think you guys will see why. Let's put chlorine on there, and put our electrophile there. And for simplicity of the discussion, now draw the benzene like that. Okay, put your double bonds exactly like mine are, and then we won't have to draw 10 resonance structures. So I am going to go ortho. And the same argument would apply to para. So ortho, I'm going to take these electrons, and I'm going to attack. And I have chlorine, I have the electrophile, and I have the plus right underneath the chlorine. which we saw happens with orthopara. Your plus gets underneath the attached group. And with most deactivators, we said, oh, this is terrible. You'd never ever do this. Halogens, this is what happens. It seems a little bit weird. Except for halogens have something none of the other deactivators have. What do you think can happen? If you have a really unstable sigma complex, what can happen, this is not the most favorable thing in the world, but the halogens are capable of donating that lone pair. This gives you another resonance structure and helps to stabilize the sigma complex. So what happens with halogens,
Does it create a double bond? Or just-
yeah, we can draw it in just a second. The plus on the carbon, what's so funny? Oh yeah, it's weird looking. We'll see it a couple times though. So with the halogens, putting the plus on the carbon with the halogen on it allows the lone pair of the halogen to stabilize the sigma complex. And that can only happen if the addition is ortho or para. With meta, it doesn't. What the thing looks like, it's weird looking, but it looks like this. It gives you your fourth resonance structure. And so that's why halogens go orthopara, because they do have lone pairs. They don't particularly like using them, but they've got them. All right? Now, when you have just one group on the ring, it's pretty easy to predict what's going on. So let's say I had, we'll do an example, and then we'll make it a little more complicated. Since we can halogenate, that's the reaction we'll do. Let's say I gave you guys this molecule. Not that one. Let's do this one. Okay, so it's an ester, and we are going to put a chlorine on it. You tell me the products maybe. So you have to find what that group is on your chart first. What kind of group is that? How's it classified? Yeah, it's an activator because of the oxygen with its lone pairs. So this is going to give us chlorine ortho and chlorine para. You give us those. So when there's one group on there, it's pretty easy to predict what's going to happen. You just figure out what kind of group it is, if it's going to be ortho, para, meta, and draw your products. Where you get exciting is where you have something like this. Let's say I had same group, but I put on, let's put on an OH, same reaction. Something like that. Okay. Now you got to sit there and think. You've got two groups that are going to both be directing. So we've got to have some rules that would help us figure out where our added group is going to go. And I think I have 3 of them that we'll talk about, and then we'll solve this problem. All right. So rule number 1. If both groups direct to the same position, that's kind of a no-brainer. That's where your group's going to go. Substitution occurs there. So that would be something like this. Let's say we had, I don't know, OCH3 and I had an NO2. And I guess let's brominate, we'll mix it up here. Okay, so you look at the groups, and you say, well, OCH3 directs ortho and para. It can't put the group para, because I've got an NO2 there. So the only choice is ortho. So the OCH3 is going to put the group ortho. NO2, how does that direct? It directs meta. Well, lo and behold, very conveniently, the NO2 directing meta also puts the group there. So we're brominating right there. Okay? This is a pretty easy choice. So we would have OCH3, BR, NO2. Simple. Okay? Let's see if this applies here. Where does this group orient?
Meta.
Meta, okay. So this group wants it to be meta. This group? Ortho-para. That's what our product's going to be. So I would put a chlorine there, an OH there. That is the product. Let's say, though, that I had done something just a little different. Just put that needle back on there. Let's say I put the OH there. Okay, so this guy directs meta. So that meta position over here is blocked. This group is going to want to put it there. The OH directs ortho-para. So it wants to put it there, or there, or there. There is absolutely no agreement at all where this thing's going to go. So we obviously need a different rule. So let's go to rule number 2. You actually do not end up with 3 or 4 products. Rule number 2 says, if the directing effects oppose, the stronger activator wins. So, what this rule is telling us is, when you analyze the two groups, I have a deactivator and I have an activator. The deactivator does not direct the reaction. That's what this is saying. So the fact that it wants to put something meta is completely irrelevant. Okay? This is driven by the OH. And that's all we have to pay attention to, because the OH is the activator. So what I'm going to end up with is still potentially a mess. Here's my OH. Cl there. And Cl here. And a Cl here. So you have still a mess, but one of these I can discount, as I'm probably not going to see much of it. On paper there's nothing wrong with it, you know, theoretically. In real life I probably wouldn't see it. Which one do you think? The second one, how come? Yeah, this is going to be very minor. And that's because you have a group in between two groups that's really sterically hindered. So it's got some steric problems. So really I'd probably only see this and this. Okay? Not in equal amounts because they're different sterically, but some kind of mixture. Now what do you think happens, this is always a question, that what if I did, let's see if I can make up a good one. Let's say I have a CH3, yeah, that's not too exciting. Let's do this. Let's put an NH, C double bond O, CH3, and let's put an OH there. Yeah, I think that'll work. This is two activators, and they're good activators. This case over here we just did was easy. I had an activator and a deactivator. There was a clear winner. Okay, the deactivator loses. But how about when you have two activators or two deactivators? Then what do? There's no real clear winner. One is not 100% better than the other one. So what happens here is you can, let's see, this guy wants to put the groups here, right? This guy wants to put the groups here. Which one's stronger?
The top one.
Yeah, the OH is stronger, so you're probably going to see more of substitution here. But you're going to see some of the others. What happens when you have two activators or two deactivators and there's no real clear winner is you do, in reality, you tend to get some nasty mixtures. But probably a little more of the stronger group activating. Okay, but it's not going to be a pretty reaction. Yeah?
So that means if you wanted something more specific, you would have to maybe change groups.
That's exactly what you do. Yeah, if I really wanted reaction here, and let's say this was a molecule I had spent 6 months building, so I'm hardly going to go and just throw away 3/4 of it, right? Because it's not what I want. What I would do is I would probably take this group, alter it, turn it into a deactivator, do my reaction, and then change it back. Okay, I'd want to do something so that I didn't have all these crazy mixtures. Okay? Alrighty. So, let's talk about today's reaction. What you guys are going to be doing is a nitration reaction on an activator. So you're going to have acetanilide, and that'll be over by the balances. I don't see it now, they must have put it away from last week. It'll be by the balances, so it's kind of a white solid. It's what you guys recrystallized last semester. Remember in the recrystallization lab? Hopefully you did a very good job, because now you're going to be using your stuff. And you're going to be taking, concentrated nitric and concentrated sulfuric acid. You're going to mix these guys together in a test tube. And you're going to keep it cold. And you're going to wear your goggles. The con acids are in the middle hood. And what this is going to generate, like we talked about in lecture last week, is the nitronium ion, NO2+. So that's your electrophile. And when all is said and done, you will have an NO2 para, that'll be your major, plus some ortho. Okay. Theoretically, you should see ortho. Most of you guys won't. And then what you'll be doing is you'll be recrystallizing. So you'll filter this, you'll recrystallize it, you'll dry it, and then we're going to get a melting point, an IR, a UV, and I don't think we're going to do an NMR on it. I think we'll just stick with those. And of course you have to calculate a percent yield too. Okay, this lab goes on for 2 days. Yes?
We have to also find the melting point for the crude sample.
Don't bother with the crude. It's going to be bad. So, yeah, the crude sample, it's interesting because the melting point's low, and it's broad range, right? But you know it's going to be low with a broad range because it's crude. So just purify it and get me one good melting point of the actual pure product, okay? I tend not to do crude melting points. It's pointless. All right, what I'd like you guys to do today, you won't have time to get through all of this by any means. I would really like for you to get to the point where you filter your crude product and maybe do the 10%, kind of washes it biphosphate that we're using or something? Disodium hydrogen phosphate. I'd like you to do that. The purpose of this is you have your product in really concentrated acids. And letting things sit around for days with concentrated acids stuck all over them can lead to some decomposition. And so if you put it into the disodium hydrogen phosphate, that's a base. And that will neutralize the acids. So what you do is you take your crude product, you put it into this till it makes a suspension. Okay, and that's just where you add enough liquid so that it's not like a gooey paste, but that you're able to filter it again. Okay? Then that will, you stir it up a little bit, and that will neutralize the acid, and then you refilter, and then you'll have your product, and the acid should be removed, and it should be safe to store it like that. So if you could get this far, that would be spectacular, okay? All right, we'll do our lab quiz next time, and then you'll just continue on next time. I really don't have much to say.